Okay. And now we will see how we will use thermodynamic tables in our calculations. Okay. So before introducing the steam power plants, we should know how to deal with the diagrams. So if I have the TS diagram of water, for example, this represents what? I have the variation of temperature with entropy. So if you look at this graph, you have, if I follow these lines, you have lines of constant pressure, okay? If I follow lines of constant pressure, just 1 second because some people are still entering the meeting. Okay, so here in the TS diagram, you have lines of constant pressures. So these are the lines of constant pressure. And you can see that inside the dome here, you have that constant temperature and constant pressure will take place at the same time. However, outside of the dome, outside of this curve, you have that the temperature is varying here while the pressure remains constant. Okay, and also here the temperature is varying while the pressure remains constant. So only inside the curve you have constant temperature and constant pressure at the same time. Okay, now what are the difference in regions here? In this region you have liquid. So if we have water here, we have the water in liquid form. Okay, and sometimes we call this phase compressed liquid. So now when we go out, when we will see the steam tables and water tables, you will see a zone where you have compressed liquids. This means that in this case you have that the pressure, okay, is much higher than the saturated pressure. What do I mean by saturated pressure? For a certain temperature, okay, let's say this is the saturated pressure. So for this pressure, I have this temperature correspond to saturated line. So as you can see, we call this line here, for this line we have the saturated phase. Okay, we call it saturated phase. And in this case, you have a mixture of liquid and gas. Okay, so in this zone you have a mixture of liquid and gas, and at the end here in this zone you have vapor, and we call this zone superheated zone. Okay, in the superheated zone you have 100% steam. Okay, so this is 100% steam. Okay, now as you can see here, okay, so let us clear because now it's not okay. In this zone you can see that if you are below the saturated, so for a certain pressure, if you are following a certain pressure is followed through these curves. Okay, if you, for this pressure, if you are below the saturated temperature, then it is a compressed liquid. And for the same pressure, if you are above the saturated temperature, then you have vapor. Okay, so for any pressure, we can define what is called the saturated temperature that we can read here. So this is T saturated. Whenever I am above this temperature, I can consider that I am in the superheated zone. And when I am below this temperature, I am in the compressed zone. Okay, and if I am at the saturated temperature, then I am inside my curve and I have a percentage of liquid, percentage of vapor. Now, how to determine the percentage? The percentage can vary from, I have here, for example, at this point, I have 0% vapor and 100% liquid. So here it is 0% vapor, while at the end point here, okay, for this point here I have 100% vapor. This is why we call this state here, which corresponds to 0% vapor and 100% liquid, this is called the saturated liquid state. So this point corresponds to saturated liquid. And the point here is for saturated vapor. Okay? Now we will see all of these again in the steam tables. So you should be familiar with this terminology. Okay. Now, what is the quality? The quality X represents the percentage of vapor in the mixture. Okay? So as we said here, it's 0% vapor, so X will be 0. And at this point, we have 100% vapor, so X will be 1. And at any point in between, X will be between 0 and 1. Okay? So as we can see here, the bell-shaped curve is the phase boundary where we have coexistence of the two phases, vapor and liquid. And inside this zone, we define the quality, which is X equal to the ratio of mass of gas over the total mass, which is mass of liquid plus mass of gas. Okay? Now, any question on this? Now here, we can see that this property X is very important because it allows us, if we know X, it will allow us to know all properties of the mixture, and we will see how. Okay. So, for example, let us say that I give you X. Okay. We will see how X can help us in finding the qualities, the properties at a certain point. So consider that you have a mixture of a fluid and gas, so water and vapor, okay? How you can write the total volume of your mixture? The total volume is equal to the volume of the fluid phase plus the volume of the liquid phase, okay? And you know that the volume is equal to the mass times the specific volume. So the mass of the fluid can be written as, so this term represents the mass of the fluid. It's the mass of the fluid times the specific volume Vf of the fluid. I should add to it the volume of the gas, which is the mass of the gas times the specific volume of the gas. Okay? Now, you know that a small v, okay, we can replace a big V by small v times m. Okay? Since small v represents big V over m, so small v can be written as mf Vf plus mg Vg over m. Okay, so if you divide all the terms in this equation by m, so if you divide all of these by m, by the total mass, what do you get? You get that the specific volume of the mixture is equal to the ratio mf over m of the specific volume of the fluid plus the ratio of m gas over m times the specific volume of the gas. Okay? Now we can replace the mass of the fluid by the total mass minus the mass of the gas. So as you can see here, you have these ratios. These ratios can be expressed function of X, because you know that we define the quality X as the mass of the gas over the total mass. So this term here can be replaced by X. This is X. And for this one, we can replace MF by total mass minus mg. Then when we divide by m, this term is 1 minus X. So you end up with the following, that the property of the mixture can be found by just doing 1 minus X times the property of the saturated fluid plus X times the property of the saturated vapor. Okay? So from now on, if I give you X, you will go to the thermodynamic table, you determine the property of the saturated liquid, you determine the property of the saturated vapor, and then knowing X, you can find the property of your mixture using the following formula. And since if you do the development here, you can see that you have the term, you have Vf plus Vg minus Vfx. This term is called in the thermodynamic tables, it's Vfg. Okay, so since you need the difference to facilitate the calculation for you, they directly give you in the tables, they give you the difference always. Okay, and as we did for the specific volume, we can do the same analogy for all properties. So if I give you X, you want to find the enthalpy, for example, you use this formula that H is equal to 1 minus X H fluid plus X times H gas. Okay, and the same for the entropy, the same for the internal energy U. This is why the quality is very important when your point is inside the curve. Okay? Any question on this? No. Now we will try to move to cycles. Okay? So what is happening in cycles? In cycles, we can change one form of energy to another form. Okay? One typical cycle that is an ideal cycle is the Carnot cycle, which is the most efficient cycle operating between two specified temperature limits, but it's not very convenient model for power cycles. We will see together why. Okay, so what is the idea of this cycle? We have experimentally proved that it is the most efficient cycle that is possible. Okay, and it consists of, as you can see here, two isotherms. So when I say isotherms, it means process at constant temperature. Okay, so you have two processes at constant temperature, and you have two other processes at constant entropy. So when I say constant entropy S, this means that these are adiabatic processes, so I don't have loss of energy during these processes. Okay, so now let us see what are these phases. Okay, now for example, if I want to talk about a power cycle, okay, what is my purpose? My purpose is to produce a certain way. Okay, so for example, what can I have from 4 to 1? If you look at your figure, from 4 to 1, I have increase in temperature and increase in pressure. This can be done by which type of devices? Which device can allow me to increase the temperature and pressure?
Heat.
What?
A heat pump or she
Okay, a compressor or a pump, very good. Okay, so I can have here a compressor or a pump, okay, for example. But we will see together, okay, that in general, if I use a pump, it's not good to have the compressed zone inside my curve. Why? Because I will have gas. Okay, and it is much difficult to increase the pressure of a gas than to increase the pressure of a liquid. This is why one of the limitation of this cycle, okay, is already that I am compressing the gas phase, which is not good. Okay. Now, let us move to the second. Just 1 second, please. Okay, let us move to the second phase. So as we said here, we can have a pump or compressor. Okay. In the second phase, I want to use the heat. Okay. So here, if you want, just before from 4 to 1, I use the pump. Okay. Now I want to, if you want to give heat to my system, okay? So I should give heat to my system in order to produce a work. How can I give heat to my system? By which process, for example? If I want to give heat to my steam, what should I do? What should I put? Which type of devices?
Boiler.
A boy.
What?
Boiler.
Yes, I can put a boiler here. Okay. If I put a boiler, then I will heat my steam and I will gain energy during this phase. Okay. I will gain Q. I will gain energy, heat. And sometimes I can gain heat at constant temperature. How? Who will tell me? How I can gain heat at constant temperature? What I am doing in the form of what I am storing. Yes, very good. I'm storing heat.
Phase change.
Latent heat. I have a phase change. And it's clear here that I have a phase change because you can see that at point 1, I have 100% liquid, while at point 2, I have 100% vapor. So this means that I have a change of phase here from 100%, and from 0% vapor to 200% vapor. So I am heating my water, okay, and this will give me energy. Now I will, in the third phase, I will benefit from this energy to produce work. So in the fourth phase, I will deliver my energy to the environment in the form of work. Who can give me an example of device that I can use here to produce work outside? What can I use?
A
Turbine.
A turbine. Very good. A turbine. Okay. So now I can produce work using this cycle of water. Okay. And now to allow my cycle to be repeated, I need to go back to the initial state. I want to go from 3 to 4. But when I go from 3 to 4, I am losing heat. So what can I use here? In this stage, I'm losing heat to my environment. So the opposite of the boiler is a condenser.
Condenser.
Yes. And in this way, I can repeat my cycle infinity of times. Okay. Now, what are the main limitations of this cycle? First, as I said before, for the pump, it's not advised to pump gas because I need a lot of power to pump a gas. This is why we will see after that in general, we try to do, as I illustrated here, we try to do this step 4-to-1 in the liquid zone. Okay. The second limitation is that for the turbine, I don't want to have vapor water droplets, okay? Because if I have water droplets in the mixture, they will harm the blades of my turbine. So this is why it is desired that part 2, 3 in the turbine take place in the vapor zone. So here it's a limitation that I have a liquid inside my mixture. And if I want to resolve this, look, as you can see in the figure here, I should go beyond the curve, my curve here. Okay, I should go outside, and therefore for my boiler I have variable temperature, which is not also practical because in the boiler in general I have a change in phase. This is why we will see together that the Carnot cycle, which is efficient, is not a very practical to steam power plants, and we will replace it by other cycles as we will see after. Okay, so to summarize, the Carnot cycle is the most efficient cycle operating between two specific temperatures, but it's not suitable for power cycles we want to deal with because first, in process 1 and 2, we have limiting the heat transfer processes to two-phase systems, which limits the maximum temperature that can be used in the cycle. Okay, so here, if you want constant temperature in boiler and condenser, you should not be above the curve, because if you are above the curve here, like here for example, if you are in this zone, then you cannot operate at constant temperature and pressure. So if your temperature is constant, you will have variable pressure during this process, which is not desired. Okay. Now, for process between 2 and 3, the turbine cannot handle steam with a high moisture content because of the impingement of liquid droplets on the turbine blades, which will cause erosion and wear. This is why, as we said, we don't desire to have this zone here inside the curve. And the process 421, it's not practical to design a compressor that handles 2 phases. So in general, if I use a compressor, it is advised to compress the liquid phase, not the gaseous phase. Okay. Now, but why Carnot cycle is important? Carnot cycle is important because it's like an ideal, it will give us an ideal efficiency that we can compare our cycles with. Okay. Now, how to calculate the efficiency of Carnot cycle? The efficiency is defined as the work output over the heat input. Okay. So here, if I take the system that I have seen in the previous slide, it's made of a compressor, a boiler, a turbine, and a condenser, as you can see here. So the net work for me is the work produced by the cycle is what? We have seen that for the turbine is producing work. It is giving a useful work. But on the other hand, for operating the compressor, I need to provide work to my system. This is why the net work output of my system is work given by the turbine minus work given to the compressor. Okay, so it's W turbine minus W compressor over the heat input. The heat input in my system is through the boiler because at this level I am giving heat. And this heat can be of several sources. We can use combustion, we can use electricity. So it depends. Okay, we can use a renewable energy process, etc. So now, but if I want to know what is W turbine minus W compressor, okay, I want to relate to heat. You know that for a closed cycle, if I have a closed cycle, what can I say? I can say that heat is, sum of heat plus sum of work should be equal to 0 due to conservation of energy. Okay, it's a closed cycle. Since it's a closed cycle, I will write the following. So it's a closed cycle. So from conservation of energy, from conservation of energy, I have the following, that sum of work, okay, equals to sum of heat, because I have that what is coming in is equal to what is going out. Okay, so here I can write what is coming, if you want, for sum of work. I have the work of the turbine. We said that a work is considered in our convention, work is positive when it's produced by the system. Okay, so I have sum of work is work of turbine minus work of pump equals to summation of heat, which is Q at the boiler, which I provide to the boiler, minus Q that I lose at the level of the condenser. So minus Q2. Okay. So this is why I can replace W turbine minus W compressor. I can replace it here by Q1 minus Q2. And I come up with the following formula, that the efficiency is equal to Q1 minus Q2 over Q1. So if I want to simplify, I get 1 minus Q2 over Q1. Okay, and as you can see, the efficiency is never 100%, and this is a confirmation of the second law of Newton, which states that I can never, for a heat engine, reach an efficiency of 100%. Okay. So here I summarize again the disadvantages of Carnot cycle. We have already talked about them, so it's just a summary for you. Now, we will see here what is the solution to the previous problems. So as we said, the Carnot cycle is not very practical. It's true that it presents a high efficiency, but on the practical level, it's not convenient for our equipment because for the compressor, we can have gas, a mixture of gas and liquid, and we said that for the pump or the compressor, it's better to compress a liquid. And also for the turbine, it's not advised to have a droplet of liquids because it will cause erosion of the blades and it will deteriorate them. Okay, so we need to come up with new solutions. What are the solutions? First, because we need to have pumping of a liquid, what we will do is that we will try to have the start of pumping at point 1, which is at the saturated liquid level. So as you can see here, if I can start the pumping effect from point 1, then the pumping will take place outside from my curve. So this means that I can do pumping in the liquid zone. This is why it will be a good idea to enter the pump at state 1, which is just at the saturated liquid level. Okay. Now, as you can see, because I am in the liquid phase now, in order to, when I enter the boiler, I cannot enter directly at the saturated phase because I am here. So what I should do in my boiler, I will have a phase of heating, of not latent heat here, of sensible heating, because as you can see here, the temperature is increasing. Then I can go through a constant temperature, constant pressure process. So here I have the latent heat. And at the end also, I want to continue heating until a certain point 3. Why I do this? Because I don't want to have liquid droplets on my turbine. So if I stop here, if I stop at this level, look what I will have. I will have in my turbine at the end, I will have a point inside my curve. So I will have droplets of liquids. In order to avoid this, I try to do more heating, because when I do more heating and I reach point 3, then when I go down, I can ensure that the point I reach here is very close to the saturated vapor. So I will have a value of the quality very close to 1. So I can avoid deteriorating my blades of turbines. Okay, so this is the Rankine cycle. The Rankine cycle has as purpose to protect my pump and to protect my turbine. Okay, these are the modification done. For point 1, it is just at the saturated liquid zone, and for the point of exit of turbine, it's very close to a quality of 1. Okay. So, any question on this here? So let us continue. Now, if you want to do a small analysis of the system, okay, this is the TS diagram of our system, and we want to calculate its efficiency. As usual, when you want to calculate efficiency, you should determine what is the net work and what is the inlet heat, the heat that is coming to your system. So here also the equation of efficiency is the same. It's W net over Qn. Okay, and if you do the analysis, you can say also, because it's a closed cycle, that sum of Q is equal to sum of W. So you end up with the formula very close to it's the same formula of Carnot cycle, that the efficiency is W net over Qn is 1 minus Q out over Qn. Okay, but now how to find Qn, Q out, and the work. First, let us start with at the pump level. What is happening at the pump level? I have W pump. Okay, at the pump level, I am increasing the pressure from 0.1 to 0.2. Okay, but I want to tell you that for a liquid, the specific volume is nearly constant. Okay, this is why we say that for a liquid, W pumping, okay, is equal to the specific weight V times delta P. Why we say this? Because in general, I want just to give you a small note before getting into this. We have seen last time together for a system with moving boundary. If you remember, last time we have worked with a piston system. So I have a certain chamber, and I have a piston that is displacing due to variation in pressure of my mixture. And we said that the work in this case, W, is given by what? You remember? By integral P dV. Okay? Pay attention. This is valid for a system of moving boundary. Okay? Now here, in my case, where I have several equipment, pump, condenser, boiler, turbine, I don't have expansion of my volume, okay? Because for each control volume, I have the same volume. But what is happening here? The work is produced in another form. It's in the form of flow work, as we have seen in the previous session, okay? So when I talk about flow work due to inlet and outlet of my my fluid, then I say that, so this is for a system of moving boundary, for a system of moving boundary. Okay, now for a system like this one, where a fluid is circulating between several components, W is given by another expression. It's integral P dV. Okay, integral P dV. Okay, so in this case, this is the case of the pump here. Okay, here I have, so I will put here, this is the case for system where a fluid moves between components. So where a fluid circulates between several components. Okay, so now if we want to
Doctor,
yes,
isn't it the same?
no, it's not the same. Yes, yes, of course, in total it's the same. Yes, very good. But look, what you mean is the area is the same. Yes, so if you do integral PdV, or if you do, oh no, sorry, here I mean integral VdP. Sorry, VdPs. I see what you are saying. Okay, VdP. So when you have a fluid circulating between several components, then it is integral VdP. Okay, and for example here, let us consider the pump. For the pump, what is happening? The pump is increasing the pressure. Okay, so here a fluid is circulating inside the pump. So if you want to find W pump, okay, it is integral of, and just I want to tell you that we should add here a minus. Okay, we will see why. Because our convention is if work is given to the system, it is negative. If it's produced by the system, it is positive. Okay, so here for the pump, you have that the work is, for this example, the work is minus integral V dP. Okay, and because for the pump, for a liquid, the specific volume is what? The specific volume is nearly constant for a liquid. This is why you can take the specific volume for the liquid outside of the integration, because the liquid in general has constant density and constant specific volume. Of course, for small variation of temperature. Here it's a small variation of temperature. If I increase a lot the variation of temperature, then it might vary. But for the pump here, for the pumping work, we can consider that it's the variation of the specific volume is very small because it's a liquid, and as you can see here, the range of temperature variation is not very high. So we can say that we will integrate between which points? 1 and 2. Between 1 and 2. Okay. So here, if I apply the formula for the pump, since V is constant, I can take it outside. So it's minus V times integral dP. What is integral dP? It's pressure. Okay, so it's minus V P2 minus P1. Okay, and of course, pressure at 2 will be much higher than pressure at 1 because I am compressing. So this will give me a negative result, and I want this because my definition for work is to count it as negative if it's provided to the system, and to count it as positive if it's produced by the system. Okay, so for the work of the pump, you can find it by simply saying that an absolute value is equal to V times delta P. Okay, I will open a new session to continue.